Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on the valence bond theory. Previously, we discussed how the properties of metals relate to the concept of bonding. You have already been introduced to the valence bond theory, and you learned how to distinguish the Lewis model from the valence bond model. In today's lesson, we will continue by discussing the overlapping of orbitals in covalent bond formation. Students, as a quick review, please state the valence bond theory and explain what the valence bonding method is used for. You may begin now.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. I am sure you had no problem with this review activity. The basic principle of the valence bond theory is that a covalent bond forms when the orbitals of two atoms overlap and the overlap region, which is between the nuclei, is occupied by a pair of electrons. The valence bonding method is used in conjunction with the valence shell electron pair repulsion method to describe the shape of molecules. If that was your answer, then you are correct. Let us continue by discussing the overlap of atomic orbitals, including sigma and pi bonds. In order to examine the detailed makeup of covalent bonds, it is important to focus on the ways in which orbitals overlap. This is because atoms need orbital overlap in order to share electrons and form bonds. There are several different types of atomic orbital overlap that lead to the formation of covalent bonds. These are the three basic atomic orbital overlaps. In image A, you can see the SS type overlap, in which the half-filled s orbitals of two atoms overlap. Hydrogen molecules, for example, display this type of orbital overlap. In image B, you can see the sp type overlap. The half-filled s orbital of one atom overlaps with one of the p orbitals of another atom that has only one electron. Hydrogen chloride molecules display this type of orbital overlap. In image C, you can see the pp type overlap. As you can see, two half-filled p orbitals overlap along the line joining the two nuclei. This is referred to as a head-on, end-to-end, end-on, or linear overlap. Chlorine molecules display this type of orbital overlap. The type of orbital overlap between two atoms, as in images A, B, and C, result in the formation of covalent bond called sigma bond. The directional nature of the p orbital can cause the overlap to occur in this way as well. The half-filled orbitals overlap along the line perpendicular to the nuclear axis. Since this overlapping of p orbitals make them parallel to one another, it is referred to as lateral or sideways overlapping. These two types of overlap account for two types of covalent bond, known as sigma and pi bonds. While valence bond theory is used to describe these two types of overlap, they are also essential features of molecular orbital theory. The SS and SP types will always overlap along the nuclear axis, hence results only in sigma bonds. Sigma bonds have the highest electron density along the bond axis in between the bonded nuclei. The bond axis is the imaginary line that joins the nuclei. The electron density of all sigma bonds is concentrated along this line. All single bonds have their electron density concentrated along the bond axis, and thus are sigma bonds. A parallel overlap had two regions of electron density. One is above the sigma bond axis, and the other is below it. As we stated before, it is called a pi bond. It holds two electrons that occupy both regions of the bond. Double bonds are always made up of one sigma and one pi bond. The double bond increases the electron density between the nuclei. There are also triple bonds, which are made up of one sigma and two pi bonds. This shows us why double and triple bonds were only considered as one electron set when we were discussing valence shell electron pair repulsion. Each electron pair occupies a distinct orbital, which is a specific region of electron density. As a result, repulsions are reduced. The strength of a bond is affected by the extent of an overlap. However, factors such as lone pair repulsions, bond polarities, and other electrostatic contributions affect overlap. They also affect the strength of sigma and pi bonds between other pairs of electrons. Therefore, we can roughly say that a double bond is twice as strong as a single bond, and a triple bond is 3 times as strong as a single bond. Students, in a moment, you will see several sentences. Please fill in the blanks with the appropriate words.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. It is nice to see you again. Let us fill in the blanks together. The bond axis is the imaginary line that joins the nuclei. A parallel overlap had two regions of electron density. Atoms need orbital overlap in order to share electrons and form bonds. Sigma bonds have the highest electron density along the bond axis. In SS-type overlaps, the half-filled s orbitals of two atoms overlap. Did you correctly complete all of the sentences? If so, great work. If not, review your notes and ask your teacher for assistance. In today's lesson, we learned about atomic orbital overlap in covalent bond formation. We discussed sigma and pi bonds, and we learned why double and triple bonds were considered as one electron set when we were studying the valence shell electron pair repulsion method. This is all for our lesson today. In our next lesson, we will continue talking about the valence bond theory. We will discuss the hybridization of orbitals. Until next time, thank you, teacher. Thank you, students.